Aha! I knew what you were thinking. Of course, this equation for electric force looks very much like the equation for the force of gravity. Good old Isaac Newton. All right, that is what we're talking about today in this video. Welcome back, ladies and gentlemen. We're going to be looking at electric force. And we will do a little comparison to gravitational force. But we'll also get into some nitty-gritty stuff regarding using this relationship for electric force. Okay, well, what do we want to represent here? Let me draw or write these equations one more time so we have them visible. We can check them out. There's the electric force is equal to a constant K times charge A times charge B divided by the distance between the charges squared. And the gravitational force. This one should look very familiar. You should know this one pretty well. Gravitational constant times mass 1 times mass 2 divided by the square of the distance between the masses. Awesome. So there's a couple things going on that we want to notice. There are similarities, clearly. And there are also a difference or two that really do matter here. First, you want to notice both forces are directly proportional to an amount of something. So with electric force, what's the amount of stuff, of something that we're dealing with? The electric force is proportional to the amount of, and the thing we're dealing with is charge. If there is more charge involved, there would be a stronger force. Well, here with the gravitational force, not equal sign, sorry, proportional. The gravitational force is proportional to an amount of something. And what is that something? In this case, we're dealing with mass. Amount of mass, right? Well, what else? Both of these forces exhibit what's called the inverse square relationship. So this electric force is proportional to the inverse of the square of the distance between the charges. And the gravitational force is also proportional to the inverse of the square of the distance between the masses. Excuse me. So that's the inverse square relationship. So check this out. If you have two charges and they're separated by a certain distance r, but then you double the distance between them, does the force get cut in half? No. If you double the distance, that doubling is also squared. So you're really having 1/4 the amount of force between them. If you triple the distance, you would get 1/9 of the force between them. Inverse square relationship. Inverse square. There you go. Both of them exhibit that relationship as well. There is an important difference between these two relationships, though. It has to do with the constants. One of them, this constant K, 9.0 times 10 to the 9th Newton meter squared per coulomb squared. Remember, capital C is coulomb, amount of charge. This constant here, capital G, this is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay, so two things are visible, evident when you look at these two constants. First, and really most important, the exponents. With these exponents, you notice that the positive 9 makes this number a very large number. The negative 11 on the exponent makes this number a very small number. Okay, this constant is very large, this constant is very small. Another thing to notice is that in the units, Newton meter squared, that's the same, but coulombs squared versus kilograms squared. You see the stuff you're dealing with in the denominator of the units here and the stuff you're dealing with there in these units. Just some things to point out, but it's the exponents and the size of the numbers, the size of these constants that really is the important part here. K is a very large constant, G is a very small constant. Now, let's make a comparison further between these two forces. It's interesting to ask a question like this. Well, could you have both of these forces acting on the same pair of objects? Could you have an electric force between these two objects and a gravitational force? Well, you have to ask yourself this. Are the two objects charged? Do they have charges? If they do, then there would be an electric force between them. Do the two objects have mass? If they do, there would be a gravitational force between them. So what if they have both? The interesting question you might ask could be said like this. Which force is stronger? And we'll look at this two different ways. Which of these forces is stronger, the electric force or the gravitational force? Okay, so first let's compare, let's make a comparison between electric charges that have the basic unit of charge, which is a coulomb. So we're going to have charge A with 1 coulomb and charge B with 1 coulomb. And we'll separate them by a distance that is a basic unit of distance, which is a meter. So we'll have a coulomb of charge separated by 1 meter. We're going to do something similar with our gravitational force. We're going to say we're going to have a basic unit of mass, which is 1 kilogram. So we'll say 1 kilogram and 1 kilogram. And we'll separate them by a basic unit of distance, which is 1 meter. So let's work that out and see which force is stronger when we look at it this way. So first, let's do the gravitational force between two masses. And each mass is 1 kilogram. And they're separated by 1 meter. So how do we work this out? I could show this by saying there's a mass there, M1, M2. Distance between them, the distance r is 1 meter. M1 is 1 kilogram. M2 is 1 kilogram. That's what we're going to do. And we're going to look at the gravitational force that exists between them. There will be a force of gravity attracting them together, right? So what is that force? Let's try to find it. So that force due to gravity right there. Well, we have the equation G m1 m2 divided by r squared. So G is 6.67 times 10 to the negative 11. And let's include the units this time. We have Newton meters squared per kilogram squared. And then M1 and M2. M1 is 1 kilogram. M2 is 1 kilogram. I'm going to get my hand out of the way for you. And the distance between them r, that's 1 meter. 1 meter, and the 1 meter is squared. So what is the strength of this force of gravity? How strong is it? How much force is created here by these two masses? Well, okay, 1 squared is 1. 1 times 1 is 1. 1 on top, 1 on the bottom. 1 divided by 1 is 1. So the answer, I can save myself a bit of math. The answer is just this number. 6.67 times 10 to the negative 11. And now the units do almost all cancel out. I have a force, which means the units I am left with are just newtons. So that is the strength of the gravitational force between these two masses. Awesome. Well, how about if we look at two charges? Let me put the diagram up on top here. We're going to have charge A, and charge B. And this has a charge of 1 coulomb. This has a charge of 1 coulomb. And they are separated by a distance of 1 meter. I want to know about the electric force between them. So, okay, here, I got to be careful. Look at this. 1 coulomb of charge there, 1 coulomb of charge there. Positives. Okay, fine. And so being like charges, we will see a force of repulsion, right? They're going to try to get away from each other in this instance, in this example. So I want to find the electric force. And that's easy enough. I have the equation handy. Here we go. QA, QB divided by R squared. This electric force. K, 9.0 times 10 to the 9 Newton meter squared per Coulomb squared. Remember, that's different, right? And over here, I will have QA and QB. That's just 1 Coulomb times 1 Coulomb. R is 1 meter, and that is squared. So what's this going to come out to? Well, you can see something right away. You're going to see, well, okay, look, 1 times 1 is 1 on the bottom. 1 squared is 1. So top is 1, bottom is 1. 1 divided by 1 is 1. I get that number. 9.0 times 10 to the 9th. And units work out so that this is a force measured in just newtons. Okay. So, when we compare two situations that are using basic units, singular units, so 1 coulomb of charge versus 1 kilogram of mass, we can see that the electric force acting on those two charges is far larger than the gravitational force acting on those two masses. This is only one way to look at this. And by the way, in terms of the numbers, if you're not really liking the scientific notation, well, you just write a 9, and that 9 tells you move the decimal point 9 places that way to make this a larger number. So 5, 6, 7, 8, 9. Add some commas so it's easy to see. What is that? 1,000, million, billion, 9 billion newtons. Oh, those charges are gonna wanna move. Well, what about this guy? We can say, we already have said that is a very small number. Well, how small? The negative 11 tells us that that decimal point will move to the left 11 places. And so, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, there. Yeah, that's hardly going to cause those masses to accelerate at all. They will experience almost no acceleration. That's tiny, because it's just hardly there. Okay. So with this type of comparison, we can clearly say that the electric force is much, much, much stronger. But there's another way to compare them, and this might make a little more sense to do it this way. Check it out. So instead of two separate situations with two separate quantities, let's look at two electrons. There's an electron, and there's an electron. Now, electrons are all negative, so these two are like charges. They will end up repelling. Let's put these two electrons 1 meter apart, so R was going to be 1 meter. An electron has a charge to it, and so that charge is going to be 1.6. I want to say 1.6. Why do I want to say 1? Yeah, 1.6 times 10 to the negative 19 coulombs. That's the charge on an electron. All electrons are the same. No matter where it is, no matter what it's doing, it's going to have the same amount of charge. So this electron over here also has a charge of 1.6 times 10 to the negative 19 coulombs. You can clearly see this is a very tiny amount of charge for one electron. That negative 19 exponent makes this an extremely small number. But there's more to it. Electrons also have mass. They're a particle that has mass. The mass of an electron. 9.1 times 10 to the negative 31 kilograms. Negative 31 exponent makes this mass extremely small. Holy cow. But it is pretty well known, 9.1. And all electrons are the same, so negative 31 kilograms there. All right, so here's what we can do. We can look at this and say, for these two electrons, we're going to look at a gravitational force based on mass, and the gravitational force will be an attractive force. We can also look at an electric force based on the charges of these electrons. Now, these being the same type of charge, it'll be a repulsive force. Electric force. And what I want to know is I want to know which of these forces is stronger, the gravitational attractive force between the electrons or the electric force which is going to repel them. Which one is going to be stronger for these two electrons? Will these electrons be drawn together, or will these electrons be pushed apart by these forces? Let's find out. So the force of gravitational attraction, let's do that first. So 0.67 times 10 to the negative 11. I'm going to forgo units to speed this up a little bit. The masses, I have 9.1 times 10 to the negative 31 kilogram. And I have also 9.1 times 10 to the negative 31 kilogram. There, those are the masses. That's a 10, sorry. And they are separated by 1 meter squared. So this force, when I get up my handy dandy calculator, turns out to be 5.52, round numbers, times 10 to the negative, you ready for this? 71 newtons. How much gravitational attraction are these electrons experiencing? This negative 71 turns this number into a 0 point and then another 70 zeros and then a 552. That is an extremely small number. They're hardly getting pushed at all by this force. But it is there. It is there. So what about the electric force? Do that in space right here. So the electric force. Well, the capital K, that constant, is my 9.0 times 10 to the 9. And again, I'm foregoing writing the units, but they are still there. They should still be there. The electric charge now, the amount of charge, 1.6 times 10 to the 19. Negative 19. And over here, the other charge is also 1.6 times 10 to the negative 19. And they are separated by 1 meter squared. So when I do that math, the electric force turns out to be 2.3 times 10 to the negative 28 newtons. Okay. So is this an insanely large number? No. No, it's not. The negative 28 means that you have a 0, then a decimal point, and then 0, 0, another 27 zeros, and then your 2, 3. Here, remember, you had a 0 and then 70 zeros, and then your 5, 5, 2. So right there, there were 70 zeros. Here, there are only 27 zeros. So, which of these numbers is bigger? You got 70 zeros after the decimal point, you got 27 zeros after the decimal point. This guy is much bigger. In fact, if you look at this properly, you'll realize how much bigger. Here's how we want to look at this. 2.3 times 10 to the negative 28 newtons divided by this answer. 5.52 times 10 to the negative 71 newtons. We're going to make this comparison. How many times stronger is the electric force? So we set it up like this and we divide. And when we do this, the units cancel out. And it's just going to give us a number. How many times stronger is that electric force than the gravitational force? It turns out that the electric force is over 4.2 times 10 to the 42 times stronger. Holy cow, right? This is a 4 and a 2 followed by another 41 zeros. Another way of saying this is 42 orders of magnitude larger than that is. It's not 42 times larger. 42 orders of magnitude larger. It's a much, much bigger deal. Clearly, the electric force will win this so-called tug of war, and these electrons will rocket away from each other very quickly because this force is so much stronger than the gravitational force. Awesome. So that's how you figure out electric force. So this was just practice with gravitational force using two masses and the distance between them. But we use this equation for electric force the same way we use this guy. It obeys the same rules. It shows you the same kind of relationship. That's really, really neat. All right. Thank you for watching. I'll catch you next time.